Then welcome everyone. My name is Jonas and I'm going to talk about Zfit and how we can extend this now to do actually bin fits with it. So a brief history on what is Zfit for anyone who doesn't know. I will first introduce it a bit and talk about unbinned fits to get you a basic idea what it is about, and then we swap to the bin parts. So a few years ago, we all know that analysis started to transition from C++ to Python. Scikit-HEP was created and we tried to create these many small packages. But one of the clearly missing parts was still fitting packages, which were mostly in C++. And there were a few smaller scattered packages, but they all lacked a bit something. So basically, we looked around a bit more systematically and just didn't find anything that was suitable for model fitting in high-entropy physics. And that's how Zfit came about. We thought there are three things we need in HEP to be flexible and have advanced features. We need to be scalable for large data and complex models. And it, of course, needs to be pythonic, integrated into the Python ecosystem. And this is very much what Zfit as an idea is. It's combining, on one hand, a well-defined API and the workflow as a basic idea. And on the other hand, it uses computing backends like TensorFlow, and in the future probably checks, that heavily speed up the computation by cheating things and by using automatic gradients. This means that pythonic, when we say that, and what it means to be integrated in the Python ecosystem, that's, let's say, the Python ecosystem as it maybe looks like a bit from the Zfit perspective. It's built on top of many of the Scikit-HEP packages. It's affiliated with Scikit-HEP, so there is back and forth. But there are also other packages that extend it, like convertable can be used, or HEPstats that is built on top, and so on. The goal of Zfit is to have a stable core package, which is meant to do model fitting and sampling from these models. The basic idea, and you will see that throughout the tutorials, we will go to some more hands-on stuff soon, is that Zfit has 5 independent parts: building your model, your data, creating a loss out of them, minimizing it, and getting a result. With that, the fit always looks a bit the same, but that's exactly the goal of it. So this is a simple fit. We will have this in an introduction tutorial, but it will always look very similar. This is now an unbinned fit, but we'll go to the bin fit very soon. Now, one thing ahead, Zfit has a strong model building part. And so it contains a lot of models like some product convolutions, Gaussians, and whatever not. However, it is also clear that all these models, I'm saying that because we won't really go into this part of it, like how to create your own models, because we know that high-entropy physics needs more than good out-of-the-box functions. And so one thing in Zfit is that you can build custom PDFs. Super easily, you can give an arbitrary shape, and the PDF then will function as a Zfit PDF and will go fully into the workflow. It has all the things that a PDF has. Integrate sample and PDF, we'll see that. And we can make it like extremely complicated. Arbitrary shapes. And one example is also if you want to use CompWA to do amplitude analysis with Zfit or anything else, this always works. So we will go through tutorials now. But keep in mind that whenever we have a model, this is maybe just a Gaussian or an exponential, but it can also be a few thousand lines of Python code that actually describe your models, and it's automatically normalized and everything. So going to the introduction, you find the links also on PyHEP site to the binder notebooks, so you can directly follow it. This is basically the workflow of Zfit, and refers to some imports, obviously. And as I mentioned, there are 5 parts. I will go through this rather fast because I think some people already know it, but there is more information there. So if you're not familiar yet or want to know a bit more, then please go ahead and see these links. The basic idea though is data just wraps data, and this should be actually pre-processed by something else like pandas or hist or whatever, and then you just put the data in. So that's not very spectacular. All we're saying here is we define what is the observable and from where to where does it go. This is some warnings from TensorFlow, but that's very normal. If you start the thing, it says it doesn't find a GPU, that's perfectly fine. And then what we can do is we can create some random data from a NumPy normal, and we have Zfit data set. Super simple. This has a few nice attributes, but that's not very interesting now. So building a model. That's, as mentioned before, probably the strongest part of Zfit. Models in Zfit are mainly PDFs that are normalized over a certain normalization range, also called norm. And they are parameterized by parameters that can later on be fit. Creating a parameter is rather straightforward, like this. And now we can actually create one of the predefined PDFs, a Gaussian, by saying what are the observables, which is the same as in the data. They, of course, need to match. And we can say what are the parameters. PDF can give us some information about what it is normalized about and everything. And what parameters it has. We use this parameter, sigma is this. We can also have simultaneous fits and multiple parameters and parameters depending on each other. So this is maybe not so clear that every parameter is just one simple free parameter, let's say. And with this, we can get all the free ones. So PDFs or Zfit models, they offer some out-of-the-box functionality, whether you make them for yourself, whether they're predefined or anything, doesn't matter. Namely, they have a PDF function, which is the normalized function that takes a norm argument. It has an integrate method that integrates over a certain range, also multidimensional. Also, if you didn't define integral, it does numerically, and it has a sample. These are basically the core parts. There is actually also an extended PDF and extended integrate, which just scales by the yield if you make the whole PDF extended. So the integration goes like that, and we get a value back. What's maybe a bit surprising is that we get something like a TF tensor, but that's something that you don't need to worry about because TF tensors or checks arrays or whatever, they're all NumPy-like structures. So for most cases, you can just treat them, as you see here, mp to the square root, as if they were actually NumPy. Or otherwise, you could also just explicitly convert them by something like mp.array, and then you get it explicitly, but that's usually not needed. As said, we can sample from it, get the values out. Sample is like a data object, nothing special. So as you see here, we get the NumPy-like values out, so you cannot just sample and use Zfit as a sample PDF. It has an accept rejects algorithm, so it will be sampling any of your PDFs. And we can use PDF. With this interface, you can also simply do plotting using matplotlib, and we can have a lot of different models in crystal ball, polynomials, kernel density estimations, conditional PDFs, and so on. But you can also add your own whenever you want. It's quite simple to do. So for a shape fit, what we would do is we can create, for example, a crystal ball. We can create an exponential PDF, and we can create a KDE as a PDF from some simulation. Then we can use some PDF to compose it. We can either use fractions to compose it and set these values, sample from it and plot it. Again, this is all kind of standard introduction, so this is a bit faster. This is now our model, the data. We can also make it a bit more sophisticated and just plot all of the components of our model. So we see how that goes, and we see the exponential, we see the kernel density estimation, and we see our signal contribution here. That's all there is. We just made a sample. We can do the same thing extended, which just means that PDF has a yield, and when we sum these PDFs, the sum of it will also be extended. Nothing special about it. Then we have loss functions. Loss functions are usually likelihoods, or also chi-square functions, which are either like that unbinned NLL, or there is extended loss and extended non-unbinned LLL if you want to take the size of the data sample into account. And then for the minimization, we can create a minimizer. There are a few available, mainly Minuit seems to be the best one. There is SciPy that is kind of wrapped, and some others kind of locked. And it's actually, side note, even fully compatible with iMinute, so you can even invoke iMinute directly if you want. And then when we have our minimizer, we can just say minimize, and we're getting our result. And we can now plot our PDF. And then it's gonna show us the result of it. There we go. We can look at the fit result, which is going to give us information about different things. We can see the parameters, and we can do some simple uncertainty estimation. We can even get actually minute out that was used. And we can do some simple Hessian uncertainty estimation, or we can do some errors like minus, and then they will be remembered in the result. This is where Zfit ends, when we went through everything. And this is where other libraries can again take over. We can make plots, or we can do statistical inference. And that's where, for example, HEP comes into play, which can calculate confidence intervals or limits or S-plots of your data. It has asymptotic calculators and frequentist calculators. It's actually a Scikit-HEP project. And with that, we can get different answers on the significance of our values. HEP though is independent of Zfit. It just uses basically the same interface. All right, that was the introduction of what is Zfit. And these are all unbinned fits so far. There is a lot more. You can do simultaneous fits. You can do toy fits. You can combine models with products and convolutions and everything. If you're interested in that, go to Zfit tutorials. The link is on PyHEP at contribution, and you can play around with that. So Zfit bit, that's the actual new part, because before Zfit was just for unbinned fits, but obviously this should be able to also handle binned fits. Now, when we say binned fits, there are two ways how people would usually probably look at binned fits. On one hand, we can have an analytic shape, and instead of fitting that unbinned to data, we can just bin this analytic shape and fit that, which is more, let's say, an LHCb use case, for example. While another way of binned fits is template fits. That's more a CMS and Atlas or semi-leptonics and LHCb use case, which often is also done using the histfactory model implemented in PyHEP. Now, the histfactory model is if you have a very specific kind, let's say, of templates, and it's kind of very limited, that's some strong assumptions. However, histfactory also solves the large use cases of CMS and Atlas. While you can, in principle, reproduce that with Zfit, this is not the goal at all. The goal of Zfit is to be an open world fitter that can just do anything, and especially it should be able to do all the things that you can't do in something like PyHEP. If you do the same as in PyHEP, it's going to be slow and cumbersome and not well tested. So that's what PyHEP is for. We again can import some stuff and go to the binned parts. Now, the binned parts in Zfit are analogous to the unbinned PDFs. Often they're just named something like some PDF is now a binned, some PDF. And there are converters back and forth. So to start out, we can see an example, an unbinned example that is just fitting a Gaussian to NumPy array. We create a NumPy array that is normally distributed, variable Gaussian unbinned negative log likelihood, and we fit that. We don't fit it here, but we can do that. This is as we've done before. Now, to go to the binned part, making that thing binned means one way to do it is simply calling to binned and saying how many bins we want. So here we have the unbinned data. We say to binned, and here we get a data object. Then we make our model binned, where we just say we want to have the same like binning as data is in. So we could also just give n bins, but let's say just to make sure that we have the same binning as data. And then we can create binned negative log likelihood just to fit a Gaussian. That's all that is needed to create a binned loss, which again, your model can be anything, your data can be anything. All that needs to be done is to binned, and both of them are binned using a binned log likelihood, and we can fit it and get the result. Again, from here, everything looks exactly the same as before. We can do histograms, we can do errors, all very much the same. And this is then our fit result, as if we do it unbinned, let's say. Now, let's look at this bin part a bit more in detail, because this was a bit shortcut to take. This is the simple way to go about it. Now, what actually happened is that our data object, which is now binned, just get a binned space. So if we can compare this and see that ops binned is binned now, and the ops that is not binned is not binned. We also actually see the binning because these spaces have now an attribute binning. That's this one here. That probably looks already quite familiar to some user. Now, this was a simple conversion, but we can do all these steps explicitly. So we can, for example, take our unbinned observable and say this observable with binning, we can give a number of bins and we get the observable binned. Or we can define a binning differently by saying regular binning using this syntax, or a variable binning. This is also supported. This doesn't look by coincidence like hist axis. This is very well on purpose. We'll just see that. And we can also just create actually a space from binning, because that already defines everything. So we get this out. Now, if you want to convert data into models, we can now use, for example, this bin variable, this one here, and say, okay, use this now variable binning to binned, and we get bin dataset. That looks a bit odd, but we choose now variable binning, and we can say model to binned, and we get the same model binned in this variable. So far, straightforward, everything can just be converted with to binned, or also to unbinned if you want to get it back. As you may have already noticed, there are a few things that are very similar to UHI, and that is on purpose. Zfit is, of course, fully compatible with UHI, or as far as it can be. So the bin data object directly adheres to UHI, and it also has a toHist attribute, so you can directly get a histogram or also boost histogram out. And binned PDF has directly a toBinned data or a toHist attribute, so you can convert them like this. So if you want to create a histogram, you create a model, analytic one, whatever, you want to have it binned, you do toBinned. Then you want to get a histogram, then you can do that, and you get your histogram. We'll plot that later on. So binned data has all the attributes that we expect them to have, like values and so on. And binned PDF is basically the same as an unbinned PDF, but it has two more methods, the counts and the relative counts. It still has PDF and extended PDF, because that's not quite the same. PDF is density, while the count is the integral or the density. And the difference is basically the bin width, which with constant binnings is just a constant factor that we need to divide by. With non-uniform binning, that gets a bit more tricky. But this is whenever you try to plot a histogram versus a PDF, that's the factor that's usually missing, because one is density to PDF and the other thing counts is the integral over the bins. And we can, as with the unbinned one, we can just sample from it and we get all that. And one of the benefits of this binned interface is that plotting now becomes a lot easier because we have NPL-HEP. And we can just plot, for example, data. See, this is a bin data in Zfit, it directly works, or a model to hist, just scale it correctly, because this is not an extended PDF. And we got this. Or we can use the sample, where we sampled from them, that the sample, so it's not exactly an Asimov data set. Or we can also plot the density. So here we use now our model.pdf function to plot the density. And we have data and density true. Oh, we don't need that hist. And we see that the response, we can also just give in X to our model, but because our model is binned, it gives us a binned response. There are also binned loss functions, namely the extended binned, negative likelihood, and same for chi-square. And we can do something different than just going from unbinned to binned. We can also directly start with the binned histogram. And this means we can create a histogram PDF just from a histogram. This is now actually a histogram. We can give it a yield parameter, and we can say this is extended using this histogram, for example. Then we get it. There are also very few, it's very limited to these template fitting PDFs that help you with modification to incorporate nuisance parameters. For example, there's a binwise scale modifier, which can either automatically create or you can manually create some modifiers. There's now a list of like 50 objects, which are all set to 1 and can freely vary. And the yield is also quite complex, actually. Note, however, that just setting this means just that we're just going to scale the histograms up and down. This doesn't constrain anything. So this is not yet a real Beast and Barlow or something. Another technique that we can use is morphing. We can have multiple simulation templates with different nuisance parameters and then interpolate between all of these. These are different histograms, and we can then use a nuisance parameter and put them into some spline morphing PDF, which we can plot, and we can also make now. We're just using the simple histogram PDF just for showcase of the fit. We can make a sum of it, which is automatically displayed if you do the to hist. We can sample some data from it, just randomly setting some of the modifiers. And now we can add constraints to it. So we say we have these free modifiers, but we don't want to keep them free. We want to constrain them Gaussian. So we want to say that these bins can vary, but just like Gaussian constraint. And we can create our extended bin NLL and actually minimize the whole thing, which is now a bit more complicated since we're minimizing something around like 50 parameters. There we go. We have a result of many parameters, and this is in the end the fit result. We can, of course, make things more complicated. And as a last feature to show is that we also can, instead of just converting a histogram to an unbinned PDF, we can, for example, interpolate with it using some splines. So we take our binned histogram, we interpolate, and we'll get this one. Now we plot the new spline PDF compared to the histogram. And now, as typically with Zfit, when it ends, we can use hepstats to do inference. Hepstats is now can use these bin fits out of the box, and it can actually also just go ahead and do multidimensional PDFs now. All right, that was the introduction into the binned fits of Zfit. So 1 second.
Thanks a lot.
So as a summary, basically where we are now, Zfit is also developing, and we got this binned and mixed API now in. The future is we want to clean up things and also change some of the things because there are still a few, let's say, design flaws that are baked in. So we will definitely continue to incorporate also feedback and adapt to other libraries. If you have any comments, any bug things, any ideas, you have a known library that want to get working with it, then please come forward. And the binned fits, they are still rough edges, and there is still a lot of extendability, of course. Yeah, thank you very much. Questions are on Slido.
Yes, I think we have a few minutes for questions left. So first, thanks a lot for this nice presentation and for filling this gap for using binned models where the hist factory template is not suitable. Maybe I can read out some of the questions on Slido. So the topmost one is about is Zfit in any way related to Minwit or iMinwit, as they are both part of Scikit-Learn, probably meaning Scikit-HEP, I think. I mean, is it built on top of Minwit or serves another goal?
Yeah, so the difference is basically they're different libraries clearly, and Zfit is to be precise just affiliated with Scikit-HEP, but it's very, very close. I think Minwit is mainly a minimizer library. I mean, it provides the whole Minwit, which is used as a minimizer mainly inside Zfit. And Minwit has a few cost functions that you can create, but Minwit, for example, doesn't attempt to do model building or anything like that. This is out of scope for Minwit, while Zfit has a strong focus of getting this whole workflow with models and everything together. So I would say Zfit is mostly using iMinwit.
Yeah, I think.
Yeah, can I comment on this?
Please go ahead.
So, I mean, in principle, you can do all these fits here. I mean, except maybe some that use the special PDFs that only Jonas has. You can also do an iMinwit. Yeah, but on the other hand, yeah, I mean, yeah, like he said. So, I mean, this model building part is not there.
Okay, thanks for this clarification. I think, yeah, what you also said already answers partially the second question that is there, which is we use the cost functions in iMinwit or independent implementations, and yeah, is it possible to share more code between the two projects?
Yeah, I mean, I can say this was my question, so because I really think we should collaborate and share a lot of code as much as possible.
So they are actually independent implementations, but you can already share quite a lot because you can use the Zfit loss function to minimize with iMinwit. So this is compatible, and also the other way around. You can, as far as I know, also take a iMinwit cost function and minimize with Zfit minimizer. So it's just the disadvantage that since iMinwit doesn't provide any models, anything that will depend on a model, like doing resampling or something, that won't work then. That needs like some Zfit. But of course, we I think you would agree on that, Hans. Yeah, we of course try to share and move things, let's say, together or unify and keep this as far compatible as possible.
Yeah, I really think that your cost function should use mine as a backend if possible, but maybe it's not possible because of this TensorFlow backend.
Yeah, exactly. So this is why it's a custom implementation, because it uses TensorFlow as the backend and it's shipped. Yeah.
Okay. I think that clarifies this, and then the last question goes in a similar direction regarding hist. So does Zfit duplicate the binning API of hist, or is it using hist under the hood?
It's currently mostly using hist under the hood. It's surely adhering to UHI, and it's currently just using the 9 things that hist provides. It creates a new dependency on it. On the other hand, I think if you want to use anything binned, you will anyway have installed hist, and this is surely, so there's no need currently to duplicate things. It uses some internal binning stuff because it is also, let's say, the bin data is a lot more limited than hist, because in the end, it's just for fitting, and it's implemented in some TensorFlow stuff, some of the operations are missing, and the stuff that you've seen like axis or the nice plots, that just uses hist. So it's basically partially using hist, a bit re-implemented because it doesn't work otherwise. Yeah.
Yeah, but wouldn't it be better just to use hist objects directly instead of wrapping this again?
And this unfortunately doesn't work, because if you want to trace through with something like TensorFlow, then this doesn't work at all, because you don't have the operations are implemented in C++ behind the scenes in hist. Boost histogram, right? So it can't go through. Actually, I tried to do that in the beginning and having a backend. So basically what we ended up is just having a bin data object, which has just a very few operations implemented. I mean, most of the operations are not implemented because use hist if you want to do that. It's more container storage that uses the API of hist or boost histogram and uses the functionality of, let's say, plotting, for example, or the axis definition of actually the